So I should then try. Does that make sense? Okay. All right. Huh? Oh, do I have to unmute myself? I think it.
think you, yeah, I think
No, I don't want to create that.
I think it's gonna be okay.
Can you guys hear me on Zoom?
Okay.
Okay, they can hear me now. Okay. So early in my PhD, I made this rather naive observation, right? So I think the hardware perception and control probably has been solved, right? But it was a naive observation, but that wasn't unwarranted, right? So, okay. So things like GAN happened, which could generate a very high resolution images during my PhD. And things like mask CNN happened, which could localize objects and instance segment from a high dimensional images, right? So looking at these results, I was convinced that the perception perhaps could have been solved, right? And as for the control, we have this Honda Asimo that was this was back in 2008 that could actually walk around, wave hands at the audience, and there are other videos of Honda Asimo actually running around and going up the stairs. So I thought that if you could get that complex humanoid to walk and wave hands at the audience, then control and hardware pretty much have been solved. And all I need to work on is the decision-making aspect of the robot. So my answer during this to the question of why don't we have this robots in our lives is this the inadequate reasoning capability. I thought that was a missing piece. So so I asked, in a search of my thesis topic, what would be a practical, important, hard yet soluble class of planning problems, right? Because I think at that moment I thought, certain class of problems that it could not be solved with the technology that we had back then. So, I thought about this question, and one conclusion that I made was that geometry is very, very important and it's fundamental. So no matter you're cooking, constructing a building, or tidying up a living room, you have to think about geometric reasoning all the time, thinking about clearing obstacles to make rooms for replacements, thinking about reachability of objects, and things like that. So so I think one of the task space that has at this extreme is the movers, right? So I used to call this problem a movers problem, because they always have to think about this problem, how to stack objects, how to pack objects, how to clear obstacles. So I had this internal lingo for defining my thesis topic, but then of course I had to change the name because the name was too close to piano movers problem, which is just going from point A to point B without having collisions. So I had to rename this. So I changed the name to geometric task and motion planning problem. And so the task here is to move the blue boxes. So if you see, if I can move the cursors, the blue boxes here into this the mover's truck, right? Into the home region. And then the idea was to pack all the objects into the boxes and then move back the boxes to the moving truck. So sort of have that mover problem built into this environment, right? And this problem is challenging because first of all, it's got this discrete decision space where you have to think about, okay, which object do I have to move in order to get this job done? And also this continuous aspect that where you have to decide, okay, I'm going to move this object, but which motion do I have to use in order to move these objects? And in particular, in environments that have tight spaces, so very little free spaces, coming up with this kinds of motion becomes extremely challenging, right? So for these reasons, the geometric task and motion planning problem was really hard to solve. So my idea was to combine learning and planning, where we use learning to guide a planner. Okay, so just like how in AlphaGo they had a Monte Carlo tree search, right, which was a planning algorithm guided by the reinforcement learning that learns a value function policy. We were applying the same intuition at a high level, but for geometric task and motion planning problems. So we have to come up with a new type of representation and learning algorithms that would fit the IO spec, input-output spec of the task and motion planning algorithms. So with this result, we were able to solve more problems than pure learning, which tend to make mistakes when they see a state or problem that they've never seen before, right? So, and we were able to speed up planning by approximately 6 times compared to the pure planner, which tend to be really, really slow because they would have to think about different consequences of different actions at every time step. So this was a result that we had in my thesis, and this is a type of the motions that my algorithm could generate. So it would clear the boxes out of the way, move boxes into the home region, and yeah, so it's thinking about the placements, motions at the same time in order to solve this problem. And you could do this in an environment that have a different geometry. So the robot is now trying to get the yellow object from a shelf into the green box. So it's again thinking about geometry and how to clear obstacles so that you could get the target object and put it into the box. Okay. So I was quite excited about this result. And so post PhD, I wanted to get this on a real robot, right, and have that mover robot operating in the environment, in the real world environment. And as you might imagine, that dream has been shattered because I had that naive observation, right, which is that perception and hardware and control have been solved, right. So one thing that I learned is that robots do not even have the basic capability to perceive and manipulate a diverse set of objects. And that was one of the observations that I made, when I tried to port this, work on a real robot. Okay, so I had to replan, right? So I had to replan and rebuild my roadmap to, designing a general purpose robot. So, I thought, I could do number 2 and 3. So number 2 is, using these skills to solve long horizon manipulation tasks. And then I was thinking about, adding semantics and common sense to that in order to build a general purpose robot. But then I realized that I'm missing that first piece. So I had to put that back in and have to think about how to build those capabilities first. And then perhaps use my algorithms that I designed during my PhD or new algorithms that we're designing at our lab to do the other second step and third step. Okay, so today I'm primarily going to talk about the first one, how we build that how we're building those capabilities. And if you have time, then we could perhaps talk about the other pushes as well. Okay, so this is rather a big topic, and I'd like to break the problem into subproblems. So I think in this research enterprise, I think there's 3 subproblems that we need to consider. The first problem is that we have a rather limited action repertoire for current robots to solve even that subclass of general purpose robotics, which is like geometric task and motion planning problems. And the second problem is this problem of representation and perception. So I don't think we have a good representation of objects that are observable and has sufficient information to do the manipulation tasks that we want. So that's still a problem is still out there. And then the third problem is generating the big data for robotics, right? So I found out that training these skills require you to have a lot of require to use certain set of learning algorithms, and they require a large amount of data. So the question becomes, how can we efficiently generate these big data for robotics? Okay. So we're tackling these problems one by one, and so let me start with the first problem. Okay, so one of the things that I observed after my PhD was that many of the commercialized robots, if you look at the manufacturing lines, they mostly are doing pick and place. And if you look at these fancy robots that are built by Boston Dynamics, it's very fancy robots, state-of-the-art hardware and control, but they're mostly using pick and place. Right? And if you look at academia, their research efforts are also in these kinds of prehensile manipulation. So there's DexNet, SIGSTOF, GraspNet kind of thing, and these are important works, right? I think these are brilliant algorithms and data sets. But the one observation that I made is that there are objects that are just simply not graspable. Okay, so for example, here the Franca Panda is trying to move this cube, right? By translating it to on the other side of the bump, and then rotate it around the z-axis by 90 degrees and around the x-axis by 90 degrees. But the object is just too big to be grasped by the gripper of the Franca Panda. Another example is shown on the left. So here we have a quadruped that is trying to move that drum roll to the target pose, right? But it doesn't have an arm, right? So it has to use something else to move that to a target pose, right? So it's going to use it has to use its entire body to manipulate that object to the target region, right? So the main question that we're trying to address here is, can you enable robots to manipulate the non-graspable? Okay. And there are a lot of interesting approaches out there, and these are, I think, great papers that inspire me a lot, especially the one by Kevin Lynch. I think his thesis has a lot of thought-provoking content to it, and it inspired me a lot. But the problem with these approaches that rely on physical modeling and planning is that because they rely on these laws of physics, they require you to estimate these physical parameters, the mass, center of mass, friction coefficient, and so on, from RGB images. And I think this is an extremely difficult task, right, by itself. The other problem with this approach is that I realized this when I was embarking on this project. The modeling the contact is still an active area of research. So the Coulomb's friction law that you all learned in high school could get you somewhere, but it's not far enough. So if you read into this literature, there's a whole bunch of modeling, sophisticated modeling that talks about how objects become deformable when it is in contact, and how there are all these modeling techniques that could deal with that. But so to model that accurately, it's a really difficult thing to do. So that was another problem with this approach. And lastly, they're just too slow, right? So if you think about this problem of generating trajectories for contact-rich manipulation tasks, right? You need to think about the discrete and continuous decision variables. So your contact activation is our binary decision variables, and your joint movements are continuous variables, right? So that makes up a hybrid decision space. And your dynamics is also hybrid in the sense that depending on which contact activations that you have different system dynamics that come into play, right? So computing a trajectory out of this dynamics and the decision space is just too difficult. So what we turn to is deep reinforcement learning algorithms. Okay, so this is work led by my PhD student Min Chan, and so we're trying to do non-prehensile manipulation, but rather than going through this careful modeling and trajectory planning, we're just going to use model-free RL to solve this problem. And the reason that we thought this was a good idea was that deep RL has proven their ability to act from a high-dimensional sensory data. So things like Atari games, they learn to play Atari games from the pixels and so on. So that's one thing that encourages us to pursue this direction. And deep RL, so in theory, they don't need any models. So if you're doing model-free RL, they don't need models. But a lot of RL algorithms out there today actually leverage physics simulation. And these physics simulation don't have a good contact modeling or accurate physics model. But with a large amount of data, you can get away with that problem, as I'll show you later. Okay, so let me first show you a video before we talk about how we did this. Okay, so here the robot, it's the same task. The robot is trying to move that wooden cube to the target region, but it's because it can't grasp it, it needs to rely on toppling, pushing, pulling. This is actually on a non-rigid object, so we only train the robot with rigid object, but it can deal with non-rigid object. This is with a human disturbance, right? And the robot could still get it to the goal. So this is a flat object that is impossible to grasp. Now it needs to do a hybrid force and position control to actually, reorient and move it to the target location. Right? And this is for a different object with a different physical property as well. And this is with a human intervention again. Right? This is an example where the robot needs to get it on top of the table, and it knows how to utilize that environment contact to bring that up. Okay, so these are some of the motions that our algorithm could generate. So, I've said all the good things about RL, but there are also the downsides, right? So first of which is that, deep RL requires a lot of data. In fact, it requires all order of billions of data in order to train these policies. So for this first problem, one of the solutions that people have found is leveraging this large scale simulation. So I started using these Isaac Gym, the GPU based simulators to generate data in a very short amount of time. So you could actually generate billions of data within a day or so and train these policies. Okay, so this is our robot being trained to topple a book out of a bookshelf, but it just shows that you can do a large scale simulation by simultaneously simulating multiple environments at the same time. Okay, and then typically using things like domain randomization, you could zero-shot transfer to the real world. Now, so that's good, but I think the second problem is a bit more fundamental in terms of, especially for non-prehensile manipulation. So previously, deep RL has been applied to context-rich tasks. So it has been applied to things like locomotion and in-hand manipulation. But for these domains, the manipulatee is always in close proximity to the manipulator. So if you think about the locomotion, the land is always in contact with the quadruped. And if you think about in-hand manipulation, the object is always in contact with the hand. Now, if you think about non-prehensile manipulation, there are situations where the robot is completely detached from the object, right? And you can't make any progress towards the goal, right? So you could, in theory, end up just doing random actions on the air without touching the object, and that could be your data, right? Which is not very useful. Okay? Of course, there's a way to fix this, which is to have what we call contact-inducing reward. So you could say, I'm going to reward the agent for getting the hand closer to the object. So that's the term that says, okay, the middle of the finger has to get close to the object's center of body. But okay, this is good, but it actually is it doesn't work all the time for different initial conditions. So if the initial condition looks like this, the closest surface to the object from the end effector is actually this location. Now, once the robot makes a contact with the location, it actually has to do extra exploration to actually put the hand on the other side if it wants to drag that object to the dark region in the workspace, right? So it becomes data inefficient if you make the ineffective initial contact. Okay, so how do we solve this problem? So to solve this problem, we made this key observation, which is that all manipulation tasks can be basically divided into two different stages. The first stage is what we call pre-contact phase, where basically you're exploring how to make a contact with an object so that you can move it to the target location, right? So I think human does this to some degree. So if you guys think about manipulating the objects in front of you, right? I think the first thing that you think about is not how you move your joints, right? It's how you're going to make the contact. And then you think about how to move your muscles and in order to move it to the target location, right? So in the pre-contact phase, you want to make the policy so that it explores different contact locations on the object. Now, in the post-contact phase, you do want to think about that joint movement in order to move the object to the target location. Okay, and it turns out this pre-contact phase is crucial for RL because it basically defines how difficult the exploration would be down the stream. Okay. So based on this observation, what we did is basically we had modularized policies. So we had a policy for pre-contact phase, which we call pi-pre, and the policy for post-contact phase, which we call pi-post. And the way we encourage efficient exploration is by having different action spaces. So this pi-pre, it takes an initial state and a goal state as an input, and then its action space is actually a classification on one of the points on the object surface that tells you whether you should make a contact with that point or not. Okay, so every time it makes an action, it is guaranteed to make a contact with an object. Okay? So, and it allows you to explore different contact on the object. Now, during the post-contact phase, your action space actually consists of now the target end effector pose and the gains for the low-level controller that realizes that target end effector pose. So we have a high-frequency position controller below this. So it's defining the target for the end effector pose and the gains for the low-level controller, so that you can actually think about your joint movements after you make a contact. And with this, so what you see on the screen is on the y-axis is the success rate. On the x-axis is a number of data points. You can sort of simulation steps equals number of data points in this case. And in blue is our decomposition based policy. Okay, and what you see on the green and orange are the ones that does not use this decomposition and just have a pi post basically with the contact inducing reward. And you can see that ours learns a bit faster than these baselines. Yeah.
How do you make sure the end effector remains in contact with the object?
So you still have the contact inducing reward, right? So after you make a contact and your reward encourages you to remain in contact with the object. Okay, so that was for with the arm, right? So, but what about the quadrupeds, right? So this is a joint work with Jaemin and who's in the mechanical engineering department of KAIST, and Seungwon, who's we were going to co-advise for his PhD. So Jaemin has this incredible quadruped in his lab that he built, and here we wanted to ask this question of, okay, how do we move that drum roll to the target pose using the entire body of the robot, right? And the challenge here is how can you simultaneously balance yourself and manipulate the object to the target location, right? And how do you learn to do both efficiently? Right? So again, here we had this policy decomposition, but this time not in a series, but in a hierarchical manner. Okay, so here we had a high-level policy which learns to output target velocity of the body in the SE2 that would move its body to manipulate the object, right? And you would have this low-level policy, right, that outputs the joint targets for the given target velocity. And the key thing here is that you need to train the second policy first, the low-level policy first, because otherwise the robot would not be able to balance itself and realize the velocity that is given by the high-level policy. So one of the things that we found was that if you don't use curriculum learning, where you train the low-level policy first, then you can't get the learning going because the exploration problem is just too difficult. Okay. So here is a little video of our quadruped using its entire body to rotate and translate a drum roll. It's using the little space between its body and the leg to reorient the object. This is with a different shape and different center, different mass, and it's using the entire body again.
You're not using any of those contact markers.
No, here we're using contact inducing rewards, but we're using and we're only using the hierarchical policy decomposition. Yeah. Yeah, this is another box, but with a different mass. I think it's a little heavier, so the robot has to give a higher velocity in order to push the box to the target region.
Was it the same with different boxes?
No, it's the same policies for all the boxes, all the different physical parameters and shapes. Okay, there's another sequence of videos, but you guys get the idea, right?
Are these reviews real time?
Yeah, these are real time. Okay, good point. Oh, the geometry. So we're not dealing with the geometry for now. But I'll show you. I'll get into that in the later slide. Okay. Mocap plus shape. So we have a flag for each of the cylinders, boxes, and so on. Okay, so the algorithmic lesson that I had from this is that the benefits of modularity, right? So I think exploration problem is really, really difficult for RL. And by using the modularity, we can actually facilitate more efficient learning, right? It enables curriculum learning, or you could design different action spaces that encourages more efficient exploration. And this is sort of a bigger lesson that I think I had, is that the modular system is just much easier to debug. Yeah, go ahead.
Yeah, I have a quick question. So like, it's very interesting to like decompose into like pre and post stage. But how do you like jointly learn those two policies?
So basically, you execute a pre-contact policy, and then you execute post-contact policy, and then you're going to get a reward, right? And based on that reward, you train both of the policies. Yeah. Yeah. Yeah.
I think the problem you're talking about is that the value function of the problem is like completely flat when you're not in contact.
Mm-hmm.
When you do it from a stretch, if you consider in contact distance stretch, we have a trick where we kind of apply force resistance. So we modify the dynamics and approximately such that we apply force resistance. Would that make things better?
Force with distance. Oh, I see. You mean the technique used in CIO?
Yes.
Oh, I see. No, I don't think we have considered that, but I think that would be an interesting approach. Yeah, so I think that one of the benefits of knowing these trajectory optimization papers is that it helps you to design reward function. Yeah, so that's one benefit. Yeah. Yeah.
For the simulator that you use to train the RL, does it make you consider the exact geometry of the robot, like including like how the body is shaped and like how it uses that little
Yeah.
model that? Right?
So the model of the robot needs to be accurate. And the more accurate it is, the easier it is to transfer to the real world. We had trouble with that, which I'll talk about in a second. But the higher the accuracy of the robot modeling, the better the transfer to the real world. Yeah. Okay, so yeah, the important thing that I learned about this is that we initially tried an end-to-end system. So just from perception to whatever the action space is, and that turned out to be a disaster, because when things didn't go as expected, we just didn't know where to start. But after we started modularizing the policies and even the perception module, we were able to track down things a lot faster. And I think it had a tremendous impact on the progress that we've made. So, I mean, end-to-end learning is in vogue, but I think modular system is just much easier to debug, and I think it might be a better way to build the initial system. Right? Okay, the bigger lesson that I had was that, okay, so here's a ×1 speed of the robot. Okay, so that was the video that I showed you earlier was 3 times speed, but this is at its original speed. And if you look at it, it's really slow, right? It's like, okay, you could do this task, but why would I give it to a robot? I'll just do it myself, right? And it's really painful to watch this. I just want to go out and help this robot myself, right? And it's like same thing in this bump domain. It's executing the pre-contact policy, and it's just painful to watch, right? So, it's just sad to watch this. Like it finally gets that going. Yeah, but so I think the most important lesson that I got from this is that, okay, hardware is just not there. Okay, so you see these fancy robots built by Boston Dynamics doing parkour and stuff like that, but the robot arms that are out there are, miniaturized version of this industrial arms, and these robots tends to have a high gear ratio, and that makes it just really, really difficult to model it accurately in the simulation. So one of the weirdest findings that we had about Frankopanda is that you give the torque in the positive direction and it will rotate fine, but when I give it in the negative direction, like it wouldn't rotate as much, right? And these kinds of things that results from gear friction are really difficult to model in the simulation. And I think there's a need to build a better arm that has a lower gear ratio, just like how we have done in the quadrupeds. So I'm actually building our own arm with my student. I know nothing about hardware. He's teaching me a lot, but I think this was one of the important lessons that we have had over this project. Okay, so that was for objects with known shapes. But what about generalizing over different shapes? So these are objects, non-convex objects that have very complex geometries, right? And we wanted to be able, our robot to be able to deal with these general set of objects as well, right? So this leads into this second problem, which is how do we represent and perceive these objects with complex geometries? Right? So here's our problem setup. So we have 3 cameras, and there's Frankopanda, and there's this toy crab, which has a very complex geometry, and you want to flip it, right? But if you think about doing pick and place with it, you can't really do it because your hand will be in collision with the table, right? So for this, the key challenge is, this representation problem. How do you represent the object states for these objects with complex geometries, right? So one thing that you could imagine doing is estimating their 3D spatial occupancy in the 3D world, because for manipulation you need to be able to estimate their shapes, and in order to manipulate it and make a contact in particular, right? So one simple solution to do this is that you have cameras, and so you're going to get a partial point cloud, right? And you can try to estimate the shape of an object by using a shape completion algorithm. Okay, so these are some of the examples of shape completion algorithm where you have partial point cloud and you complete it into a complete shape, right? So the idea is to pre-train a shape completion network where the encoder takes in the partial point cloud that'll give out some latent representation Z, and then the decoder would estimate the complete shape of the object, right? So we could just take this part and then just hook it up to a policy, and then the policies will start giving out actions because Z now has a sufficient information to predict the shape of an object. Okay, so this was our first thought, right? Now the problem is, I think these shape completion or estimating the shape of an object is usually an overkill, just like how I think the poses are an overkill for object state representation. So the reason is depicted with this figure here. So let's say you have a toy chair that you want to manipulate, right? What really matters to you is what are the contactable surfaces on this object, right? So what part of this object would make a contact with the environment and your hand, because that's going to determine the motion of the object. Now, there are other parts of this object which are marked with gray that are not in contact with, that will never be contacted with the hand or the environment. These parts don't really matter, right? Yet, the shape completion algorithms try to complete the shapes in these areas too, because otherwise they're going to be penalized by their loss function, right? So, okay, so then shape completion seems to be an overkill. What would be a good representation for this, manipulation, right? And since we're using RL, we asked this question of, what if we had this observation that the grid representation should be able to distinguish high value states with low value states, right? And we thought about, okay, what would that be for manipulation, right? Okay, so what we figured out is that the presence and location of the contact is crucial for robot manipulation. Okay? So here's an example. So here the robot is trying to topple the cup, right? And one of the figure on the left is it's near the cup, but it's not making a contact, right? So if it moves its hand to the other side, it's not going to be able to topple the cup. But if you move down a little and make an actual contact with the object, then you're going to be able to topple the cup, right? Same thing here. So here you're trying to move that Lego block to the right, to the darker region, and if you push it with by making a contact like the one on the left, you're going to be able to push it to the region. But if you make a contact at the top, then you're going to actually end up toppling the object and not moving the object to the target location. So our strategy was to design a pre-training task so that we can estimate the location and presence of the contact between the hand and the object. So this is work by Jamie, who's a PhD student at our lab. So the idea is that you're going to have a pre-training task where you're going to take the full point cloud, patchify it, right? So you're going to patchify your point cloud, and each of the patches would create tokens, right? So each of these tokens are basically a patch of an point cloud, and then you're going to put it through a transformer, which was going to give you an embedding that is that is created by doing a cross attention with the hand state as well, right? And then you're going to have a contact header that predicts collision at that patch. So each of the embeddings tell you whether you have a contact at that patch or not. So the example is shown on the below. You have a red patch which is in contact, blue which are not in contact, and that's the sort of the labeling that we gave to the robot. Right? And then we're going to connect it with the policy along with other inputs that has joint information, the goal, and stuff like that. And this turned out to be a better choice than a shape completion pre-training. So here are some results. So it's trying to flip that toy crab, and it's actually using the geometry of the bottom of the toy to actually flip that object. Here's dragging a thin thin paper, right? These are one of the hardware ones that has rolling dynamics. So it can actually, so notice how it's using making a stable contact when it's uprighting the cup. Same thing with this guy, because there's a chance that if you push it too hard or makes an unstable contact, then it's going to roll out of the workspace. This is another rolling dynamics. It's pivoting it. This is actually an empty box that moves a lot whenever it's, yeah, it's giving that last little push. And then this is lifting a sauce bottle, but when it lifts it, it actually provides a support with its hand, so that the bottle wouldn't topple over. That tend to happen with that sauce bottle. So moving the, this is one of my favorite. It's actually using the hole at the top to lift this heavy cup, and then putting it to the target location. And you can do this for general shapes of objects. Okay, so this idea of we call it CORNs, context-based object representations. We're extending it to multiple objects. So Dongwon is another PhD student of mine, and he's been doing it with the entire scene. So what you see on the third row is the camera observations, and we're observing the world. What you see on the bottom scene is the robot's latent space interpretation of that observation. So it's reconstructing those shapes in this latent world. And the good thing about this representation that is trained based on context-based task is that you can actually use it for planning. So here's another example. So here we have the transparent objects that are observed through RGB cameras. The second column is an estimation of their shapes and locations. And we can actually write a grasping code based on this contact detection and rejection sampling to generate a path in this latent space as well, using an RRP based on the contact detection neural network that we've pre-trained. Okay, and then you can actually realize the prehensile motions in the real world, zero shot when we use that latent space plan. Okay, so this is moving the transparent objects based on its perception and motion planning in the latent space. Okay, so that's that. So we've so these are some of the works that we've done for these first two problems. Now I'm going to talk about the third problem, which is how do you generate data for this? Yeah.
I
Okay.
have a quick question
Yeah.
about the architecture. So
Mhm.
you said like it's a cross rotation with the head state
Mhm.
for the representation, right? For the policy, is it also transformer or
Policy is also a transformer. Yeah.
is there a reason why you guys use the transformer for the policy? I would imagine like if you had the representation correct, then like
Because it's a multiple patches, right? It's a token. Each of the patches become a token, right? So the embeddings becomes a token for the policies transformer. Yeah. Yeah. Yeah.
For the modeling the objects of different shapes, and I see you're basically giving the goal as the pose of the objects.
Yeah. So the goal is the relative pose.
relative to the pose.
Yeah, to the initial object configuration.
And what kind of objects did you train the policy with?
So I think we've taken the data from the internet. So everything has been trained with the shape. I think. Okay, don't call me on this, but the 3D assets that we downloaded from the internet.
So all
Yeah.
the objects are novel to the algorithm.
Yeah. So what it sees in the real world are all novel to the robot. Yeah. Yep.
Regarding the work of color, can it generalize to different surfaces with different frictions?
Oh, different frictions, yes, but environment geometries, different environment geometries, like the ones like here. I think that we need to come up with a way to represent environment geometries somehow, and we're working towards that. Yeah. Okay. All right, let me move on. Okay, so big data for robotics. So I've said this, GPU-based simulation and large-scale simulation is good for learning these manipulation skills, right? But what we found was that it's too slow in simulating non-convex objects. And so this has to do with the fact that, so this is Isaac Jim simulating moving bucket that has a non-convex objects in it. Let me just show it one more time. So with 8,000 environments, it can do this movement and simulate it quite fast, right? But when you go to 10,000 environments, it actually slows down significantly. So this is the same setting, but at a much slower speed for these larger environments. And the reason for this is that the contact detection algorithms that exist that we use in the simulator is just too slow for non-convex objects. And this is because the contact detection algorithm itself cannot leverage the parallel computation provided by the GPUs. Okay. So what we wanted to do is to fix this. So we wanted to come up with a new contact detection algorithm that can actually leverage the parallel computation that is given in the GPUs, right? So one solution to do this is, given all that work in our context-based pre-training, we could actually use a neural network to train a neural network to predict collisions, right? So you could actually take the point clouds of the object or any other shape representation you want, put it in through an encoder, and then have a collision predictor to predict collisions. And you could do this very, very fast on using GPUs because it's just neural network prediction, right? Okay, but one problem with this approach is that you need a lot of 3D assets to train this, and 3D assets are expensive to generate, right? So our intuition, or Pongwan's intuition, was to exploit the what we call local similarity. Okay, so if you look at these two pairs of objects that are in collision, right, they have completely different shapes, right? So one on the left and one on the right, pairs on the left, pair on the left, pair on the right are completely different geometries at a global level, right? So you would think that you need different data points to train this collision predictor, right? But if you look at close at the local region where they're in contact, right, they look surprisingly similar, right? So this is kind of a local similarity that we wanted to exploit in training our collision predictor, so that we wouldn't have to use a lot of 3D assets. So here's our architecture. So we would take that partial point cloud, put it through an MLP, right? So put it through an MLP, and then we would both voxelize it, right? And you put the features into the locations that corresponds to the XYZ location of the point clouds, right? And then you're going to put it through a 3D CNN, and then you're going to have a shape embedding, where at each of the voxel cell, you're going to have features that corresponds to the that point at that XYZ location. Okay? And then we're going to take that shape embedding, transform it according to its poses, right? And then extract the local features at the contact, right? And then we're just going to predict collision just based on those features at that local region, right? And this happens to be much more data efficient than the one that does not use this locality. Okay. So here's again the video of Isaac Jim using their own contact detector in simulating 10,000 environments. And here's our result with 30,000 environments with the same setup using our collision detector. And this is another set of non-convex objects being simulated in a large number of environments. Okay, so this is the result that we were able to get using our own contact detector. Okay, so that covers the first bit of our roadmap, but I don't think we're there yet. We're pushing in different aspects of this step one, and we're doing we're developing algorithm for the second step too, right? So so I think one of the things that we did recently at our, which we're going to present at Coral, is to actually extend my thesis to POMDPs. So here we are doing that learning to guide planning, but in the case where we have uncertainty in the sensory data. So this is robot trying to reason about uncertainty in shape and location of the objects to solve this task of fetching an object from the shelf with a camera. Okay, so so that's all I have for today. I haven't had a chance to talk about number 3, but I'll be happy to chat offline, and happy to take any questions that you might have. Yeah. Yeah.
Regarding the first part, in the first you said that there's a pre-policy that detects the contact point. Then is the contact point generated from other methods, such as from CDK, what you mentioned in the last part, or whether it is defined or predefined for the object?
So we train everything in simulation, right? So you can, if you're in simulation, you have a mesh. You can get the points from you can sample the points from the mesh.
Also, you just randomly sample.
Yeah, exactly. Yeah.
So for the pre-contact policy and the post-contact policy, is it predefined that it's only going to execute one switch?
Yeah, exactly.
Post?
Yeah.
So
Yeah.
in some of the videos, it seemed like once it makes contact, it really doesn't break it. It kind of like swirls the flapping around. Which is pretty interesting behavior. But then on the other one of toppling it over the obstacle, it actually looked like it was breaking contact. Was that's just the post-contact policy? Yeah,
that was just the post-contact policy.
It has its own ability to slightly break contact.
Yeah.
Have you thought at all, or do you think it's important to enable more flexibility at like the discrete switching level?
Yeah, we actually thought about that. So maybe there should be a higher level policy that determines which to use at a low level, the pre-contact or post-contact. But it turned out to be unnecessary, at least for the objects that we've dealt with. Maybe if the object is big and you can't explore with your Gaussian policy, then you might need that. But so far, we haven't seen that need yet. Yeah.
I was just thinking about the first part. Like you said, its exploration is with RF because the reward function is too sparse sometimes. So would it make sense to like give some sort of some kind of because like otherwise we have to come up with either anti-dominant policies or anti-dominant reward functions. Does it make sense to have some sort of intermediate feedback or something?
So intermediate feedback. So I think you're right that you could give a intermediate reward. And I think there are two ways to do that, right? So one is actually to design the reward function in the beginning, right? And then have that as a dense function, right? That could give you reward at every time step. The other one is that leave that sparse reward, but use, I don't know, human in the loop to give the feedback. Or I don't know, nowadays I think people try to do it with LLM. So I think there are multiple ways to do that. In this case, it just turns out that the reward function that we had was sufficient. Yeah, and it wasn't that complicated, right? It's trying to match the object pose to the target pose, and it's trying to get the hand closer to the object. Yeah. Yeah.
I think it's harder for reward function design. I think it's harder in this case. In the sense that actually reference blocking it's not structured in the same way as the reward qualities and language model to derive a reward function. Different. So reason for his test to be so hard is because first of all, like the kinematics is hard to describe by the semantic language. That's why I think he was using the composition of the policy to compensate for the sparse reward.
I think the challenge, if you want to use an LLM, I'm not sure if we're going to go down that route.
He was mentioning the Eureka that was using the large language model to propose reward function.
Yeah.
So it has to be semantically meaningful, the dynamic has to.
Yeah. So I think the challenge there is, can you actually describe the current world state in a language, right? I think that's the real question. I mean, that's, from pixels to predicates, can you go from pixels to language, right? So I think unless you can solve that problem, I think it might be very, very difficult to use these kinds of Eureka thing. Yeah.
Should we use your thing instead of GJK?
You should, I think. If you're using a GPU-based simulator, I think you should.
Oh, we're not.
Okay.
Oh, I see. So that's an interesting question. In a planning, like, is it? But it might be faster than GJK, even just in normal CPU planning-based usage.
Okay. So there's a plot that I didn't show you, but GJK allows you to trade off accuracy with computational speed. We don't have that luxury. So I think it depends on your usage. So if you need a really, really accurate contact detection with a sacrifice in computational speed, then I think you should go with the GJK. But if you're satisfied with okay-ish contact detection, then you could use our neural network. Yeah. Yes.
So some of these tasks I'm looking at it, and it seems that it could be also possible that some of, for example, like a cup is designed because humans have 10 fingers and it's optimized an object for a human to lift it up. Could it be possible that in some of the hardware applications, like you're only giving this robot, I think like two, what do we call it, kind of 2 fingers to do that same task? Could it be much more efficient if you have a robot? I know that's difficult to have like 5 fingers to grab a cup and then move it around.
No, definitely. I wish I had those fingers. Really, like I think the hardware is a limitation in learning these manipulation skills, and I think one of the like even having high degrees of freedom, I don't think that matters too much in these learning manipulation policies. If you can simulate your hand, and if you have a hardware that has a low sim to real gap. I'm saying this because I see the reasons one of the reasons I think the quadruped took off and locomotion took off is because they had this hardware that had low gear ratio, that had a very low sim to real gap, right? So if you could do that with a manipulator too, I think you could definitely do that and use different forms that is more fit for human the everyday objects that humans use.
So it could be possible because I'm going back to Wayne, the first question, can we have these robots in our daily lives? Could it be possible that we define tasks that we want a robot to have, that we actually change the shapes and design of certain objects in our world for these robots to easily manipulate instead of keeping the human-centric design of objects?
Okay. Yeah. So you want to change the environment instead of a robot? Is that your point?
Yeah, I mean, so like if it's possible that we are designing a humanoid robot that has the same structure of a human, then maybe we can keep our case. But for certain tasks, if you want to automate that, maybe it could be a better solution to change that environment to optimize for that physical robot. I mean, it's just a simple.
I think that's just task dependent. Like if you, what your objective is, right? So I want to build a general purpose robot that could operate with human made objects that are built for humans, right? So that's why I'm dealing with this. And I think it's much cheaper to change the robot morphology than change all the environment settings that we have in human environments for the robot. Yeah. Yeah.
So in learning the representation for the test, it seems that if you're training the representation based on task you have, then it's also a more difficult problem to transfer to representation.
Okay, define task.
Like for example, in that case, when you're trying to grasp a toy chair, there's some region that it can't reach. If you're using the toy chair to do something else, then those gray regions.
Yes. So that's definitely true. So when we're actually extending it to multiple corners and trying to use it for a general purpose plannable representation, we're not actually training it with hand object collision, but with object collision too. So it can actually detect object collision as well. Yeah. Between objects. Yeah.
I just wanted to query your thoughts on one of Marco Hutter's like trick for getting the reducing the symptom wheel gap in actuators was just to learn the residual dynamics or something. Would that solve the problem for you? Could have kept better hardware if you had. So
I would say you don't even need a series of elastic actuators and residual physics if you built your hardware right. So this is something that I learned from Chaemin, who built his own quadruped. His quadruped is actually built with linkage transmission system, and that turned out to be much more easier to simulate. So for him, like its simulation is directly transferred to real robot. There's no residual, signal that he learns, anything like that. Yeah.
Well, then, so you're designing. I mean, it's interesting, right? That we've rejected the idea of designing the cups so the robot can manipulate them, but we've accepted the idea of designing the robot so the simulator is good.
It's a
different choice. I understand.
It's a cheaper choice to make. I think in my opinion, yeah.
And you're the engineer in the robot case, right?
That's right. Yeah. Yeah. Any other questions? All right. Thanks everyone for coming.